I'm excited to introduce Perry Babb. He's going to talk about the KeyState natural gas synthesis and CCUS project. It's locally a pretty zippy system they're putting together, and being from Central PA, I'm very excited about it. Now, Perry's background is he serves as the CEO and chair of KeyState Natural Gas Synthesis, LLC, and leads the development team for $400 million low carbon hydrogen, ammonia, and urea production facility proposed for Clinton County in Pennsylvania. Perry is a sociologist by training, and he would say a problem solver by nature. He's got 40 years of experience creating a wide variety of successful corporations and nonprofits. He's a Central PA native from right by State College, Pennsylvania, but he also splits time in North Carolina. And very interesting gentleman, speaks 6 different languages. He's published in 6 different languages. So with no further ado, I'll present Perry Babb.
Good afternoon. It's great to be here with you. Let me get my screen shared here. It's particularly good to be with you when you have good news. You know, we can be a bad news industry sometime, you know, and it's great to have a topic and an opportunity to share some good news. Can you see my screen okay and hear me okay?
Yeah, we can.
Terrific. Well, I'm going to do my best to take about 25 minutes and then leave plenty of time for questions. My title today was a low carbon future for natural gas, but I think it's particularly appropriate to think of this in terms of midstream opportunities in this low carbon future. And it is an opportunity. Like you know, the old guy says, an opportunity is not a win, it's just an opportunity. But man, it's good to have an opportunity, especially in these days. And this opportunity is in the context of a new, next maybe, energy revolution that Pennsylvania is entering into. You know, we were a part of the, you know, the oil revolution, the steel revolution, then the unconventional gas revolution, and then it looks like we're going to be around the cusp of this new low carbon revolution related to energy. And it's going to be a bridge, this revolution, between job creation and climate concerns, economic development and emissions reductions. You really can do both at the same time. And the quote, fossil energy and quote, hydrogen economy, a bridge between those two. So what I want to touch on is basically 6 points or 6 areas. I've got way more slides than I'm going to share on, but I wanted to provide this as background information for you and use our project as sort of an example of some of these points as we're going along. As you all know very well, Pennsylvania has this amazing natural gas asset, just mind-boggling what's happened in the last decade. And the impact, not just on the basin or Appalachian Basin, but on America, on energy independence, it's miraculous, you could say, in so many ways. Its effect geopolitically, you know, we don't depend on people who hate us for oil and gas anymore. And it's just been amazing. Well, equally, perhaps equally amazing is the geological asset that we have, the storage asset that we have, and which is the part of this next revolution is going to be maximizing our storage in the way we've maximized and are maximizing our gas production, oil production. So as you can see from this image, there's a lot of parallels, this footprint of this good geological storage for CO2. It looks a lot like the Marcellus Appalachian footprint. And there's been 2 studies, extensive studies quoted here on what this storage volume potential is. You know, one's saying 150 years of carbon storage. If we took our emissions now and we stored those, we'd have 150 years worth. And another study says hundreds of years worth of CO2 storage capacity. We're located in north central PA in Clinton County, as was mentioned. And for our project, which is a small scale, really CO2 emitter, and taking our own CO2 and storing it on site, and we'll be focused on the Oriskany. But many around the table, around this room, are very familiar with Oriskany and other formations, and are very familiar with storage, of course. The implications now of this revolution related to geological storage and this idea of associating gas production and moving gas around, storing it, associating that in our thinking with using carbon and capturing and storing carbon, thinking of those as kind of a 1-2 punch. And the most obvious reason why that's important is because it's the same know-how, skills, workforce, equipment, a lot of times, that has done the impossible in producing natural gas and unconventional gas and oil production. It's the same skills that are going to be used in this new carbon capture storage industry. And that's really the opportunity, first opportunity I want to mention and to focus on is that's the opportunity for us, and particularly in this conversation here, for capturing carbon being provided to us either to move it or to store it as an industry. And there's opportunities that could be unprecedented. So there's probably two sets or two ways, two angles you can look at this, the implications of this that we're talking about. On the left side here, we're talking about a low carbon power generation and a low carbon heavy manufacturing that results when you capture CO2 off of those emission sources and store those in Pennsylvania or Appalachian geology. And the result is a low carbon product. Then on the right side, when you take and produce hydrogen, and yes, the hydrogen economy is supposed to have been coming for the last 30, 40 years, but really there's unprecedented traction and attention to hydrogen right now. And fortunately, that hydrogen, the vast majority of that hydrogen today is produced from fossil energy, like 98.5% or something. And there's a real advantage to using natural gas to produce hydrogen, ammonia, et cetera. But by capturing the CO2, you end up with a blue product, a blue hydrogen. And so the other side of this equation, one side being carbon capture, the other side being producing hydrogen from natural gas, also with carbon capture. And then that, quote, blue hydrogen can be used for power generation, steel manufacturing, ammonia production, in our case, and it can be moved around, by truck, obviously, compressed and liquefied, but by pipeline, it's likely to be moved as a blend for a while with natural gas or eventually dedicated hydrogen pipelines. Many of you are familiar with this color scheme related to hydrogen. You can use the same related to ammonia. When you use fossil energy, use natural gas to make hydrogen without carbon capture storage, that CO2 is emitted. This is referred to as gray hydrogen. Blue hydrogen is when you use a fossil energy or use natural gas, in our case, to make hydrogen and ammonia, but you capture CO2 and store it. It's referred to as blue. And then when you make hydrogen from a completely renewable source via electricity and electrolysis process, that's referred to as green hydrogen. So when that hydrogen is produced through electrolysis, there's obviously is no CO2 emission. Identical molecule in each one of these cases of hydrogen. Gray hydrogen, blue hydrogen, green hydrogen is the exact same hydrogen molecule, but the issue is what kind of CO2 was generated and emitted in the production of that hydrogen product. If these three hydrogens are combusted, the same emissions profile, basically water, really, but no difference there. The issue is how it's manufactured. In our case, we have some significant strategic advantages on proximity to big customer regions. And this applies to hydrogen, particularly I wanted to show first here. We're right in dead center of PA, north central PA, like I said, just above Interstate 80, and have a significant central location to a lot of population centers. So, I've talked about this and may refer to this in one way now, but I really want to talk about it more in terms of barriers to rapid growth in these two sides of power generation. And this is still in the implications of carbon capture storage, the context of this. So when you're making power in this revolution in power that's coming, low carbon power that's coming, it's either going to be made from a fossil energy, of course, or made from renewable energy through wind and solar, primarily some biomass, continuation of some hydro, of course, and to make renewable electricity. And then low carbon electricity is going to be generated through a continued use of fossil energy, but with carbon capture storage. And for my thinking is, I think of this as base load power, blue, green power is variable power. And, these have to go hand in hand. And no matter the level of passion about moving to renewable electricity, this is where reality strikes, is that you can't have all renewable electricity. You have to have that base load for when the wind is not blowing, et cetera. And this is the easiest way for me to think of in terms of as a base load and a variable power. So the key point here of rapid growth in this low carbon power generation on the renewable side in the Northeast, particularly North Central, particularly the Appalachian Basin specifically, we have some real disadvantages over some other parts of the country in generating renewable electricity. Obvious one, sunshine. You're right. I'm in Hatteras right now in the Outer Banks, one of the sunniest places east of the Mississippi State College, where our businesses are in Belfort area, one of the cloudiest places east of the Mississippi, right? Real contrast. And so there's some, natural disadvantages over southwestern U.S., of course, or part of Texas for wind power generation. So that is going to give additional advantage to natural gas for the production of hydrogen, just because of the amount of renewable electricity is required for electrolysis for hydrogen ammonia production. It's a gargantuan amount, and it really has to be excess renewable electricity. And we're a long way away in Pennsylvania, for example, of being close to having excess renewable electricity, really 2 cents or less a kilowatt hour before it becomes close to being competitive with making hydrogen from natural gas and storing the CO2. Now, the other part, way to look at this is in hydrogen production. Likewise, you can make it from electrolysis, or you can make it from fossil energy. And I'm talking specifically here about using natural gas. And you can use, it's the same hydrogen molecule, remember, but the barriers to scale up and cost barriers are significant. Significant capital cost decrease has to be realized in electrolysis units and deployment for green hydrogen to become cost competitive with blue hydrogen. Essentially, the power has to be almost free, 75% really reduction in capital cost. And I'll show you some data points in a second about this cost advantage. And that's where we get to next in the implication of this move that I believe we're in. Here's some IEA cost projections. These are fairly recent in the last 2 years. Same data points today, hasn't changed dramatically. Still the objective, everybody's talking point is $1 a kilogram hydrogen, and that equates to about $6.50 an MMBTU of energy. And right now with natural gas, on the left, you can see, with $3 natural gas, you're under $1 a kilogram. For hydrogen, you add in carbon capture storage, it's about another 50 cents. Of course, if you have your own gas, like in our situation, we vertically integrated the gas production into the business case. So ours are, at cost, the gas supply for that hydrogen production, and we're storing the CO2 on site. So we're well below this $1.50 a kilogram cost. So you can see for green hydrogen over here, the best in the world right now is approaching $3 a kilogram. And that's where North Africa basically unlimited gargantuan volumes, oversupply of renewable electricity to get to that cost point. But more typically, we're talking $42 an MMBTU is the cost of green hydrogen in most parts of the world right now. This is going to definitely come down. But like I was talking with somebody yesterday, blue hydrogen and its cost advantage is going to make markets for green hydrogen as those prices come down. Here's some good, solid variety of projections of where hydrogen demand is going to go to. In 2018, it was, here just under 100 million standard ton of hydrogen. Shell believes that by 2050, it's going to be 85% more than that. Jump over here, the IEA believes it's going to be 300% more than that. All the way over here to Hydrogen Council thinks it's going to be 600% more demand by 2050, and it being a huge part of the overall energy mix of the US. And there's the reality is that it's impossible, utterly impossible to reach that 600% or half of that only with green hydrogen. Blue hydrogen will be integral to this for decades to come, and that's the opportunity. I won't belabor some of these, but these are some data points on hydrogen capacity now and how it's projected to grow, some outlook numbers. This is really important, comparing hydrogen produced with natural gas in the US as opposed to other geographic areas. You can see over here on the left, a great cost advantage. And this is based on a $3 an MMBTU. On the bottom right hand of the screen, you can see cost of gas. And of other parts of the world, think Europe, where there's a hard drive toward hydrogen right now, sure is an opportunity for us to export hydrogen and probably ammonia as the hydrogen carrier to the European market for decades to come. That's not tomorrow that market's going to open, but that's on the horizon. But you can see we have a cost competitive advantage because, again, of our natural gas, and that paired with our great geology for storage, it gives us a competitive advantage that's significant. Let me check my time here. Okay. This is a good graphic to show the economics, but this is focused on ammonia. Ammonia is talked about as a carrier of hydrogen. It's a lot easier to move around. All this ammonia infrastructure already in place, many dozens and dozens of ports that handle ammonia around the world. It's handled in agriculture and industry. Much easier to move around than hydrogen. And for some applications, it's likely that what will be exported, for example, from Philadelphia, could be Pennsylvania natural gas, hydrogen made or ammonia made from that natural gas, and capturing the CO2 and storing it, and that being exported as marine fuel. The Japanese are deploying it, combining it in their coal-fired power plants, and they're going to transition those coal-fired power plants to ammonia-fired power plants. You've read a lot of that in the news just in the last 6 weeks. And I forgot to mention that some of this is focused on the economics around carbon capture in the US right now. It's absolutely dependent upon 45Q tax credits that have matured the last 3 or 4 years, and particularly the last 6 months. Some rules have been clarified, and I'll get to a couple of those in a second. But the economics in some parts of the US without accessible close by geological storage, these are tough economics with the 45Q. For Pennsylvania, the Marcellus Appalachian Basin, because of the geology, we're going to have some opportunities, all different kinds of sources of emission and capturing CO2. One example of this is 45Q rules that were clarified at the beginning of the year. And really what this does is allow several manufacturers that don't meet the threshold minimum of carbon to be stored to combine those volumes together and count toward the 45Q, and then put that into a common the pipeline to a storage location. But this allows all different kinds of businesses, large businesses, to be candidates for and to consider carbon capture and storage for the future. That the financial underpinning would be there with 45Q. So let me talk a little bit about our project and to illustrate some of this. So as was mentioned, it's in a very rural part of Clinton County, which is terrific when you're building this kind of plant because it's not concerned of you're in a neighborhood or next to a neighborhood and, you know, what kind of plant's that going to be, what kind of emissions there. You know, we're on a 7,000 acre tract, contiguous, one owner pretty much for that 7,000 acre. 7,000 acres, to put in context, that's 10 miles by 10 miles by 10 miles by 10 miles. Humongous area, and which gives us both the opportunity for this greenfield manufacturing site and to explore the CO2 storage potential of that site while we're also producing the gas. So we're going to make 3 products, blue hydrogen, as we've talked about, and as you know, the gas synthesis process, you put pressure and steam to hydrogen to make ammonia, pull nitrogen from the air, to make hydrogen, pull nitrogen from the air to make ammonia. And then we further take that in our second category of products are emissions reduction products. And we use that ammonia combined with some CO2 to make diesel exhaust treatment, DEF, was mentioned earlier, and other kind of power plant exhaust treatment. So we'll capture we'll use first about 170,000 tons of CO2 in our DEF production, but that's off of a process that's about 50% less CO2 being emitted. We'll store 100,000 tons of processed CO2, and of our combustion, post-combustion CO2, looks like we'll get about another 80,000 tons. This is some of our gas usage, and like I mentioned, 7,000 acre. So our business case is built around integrating gas production on site, manufacturing on site, and carbon storage on site. Integrating the business case, the cost there, integrating the capital costs related to producing gas, storing CO2. So we have this little laboratory at commercial scale to prove out some of these things and to, you know, hopefully learn some good lessons, maybe not too hard of lessons that others can benefit from also. As I mentioned, the gas, 7,000 acre, 250 BCF of gas, Marcellus at the track. My partner in the project and the gas producer is Frontier Natural Resources. And part of the motivation of all this was we have stranded gas, you know, and what are we going to do with it? We have a 35,000 gallon a day LNG facility now, but that just is a pittance of the gas to be used and taken away. So we had to find a way to make something with the gas on site. And which has led us in this direction. So part of what we're working to prove out is that in the same track, we can think, and this can be extrapolated to the rest of the room, think in terms of this same geology, there's a utilization of an asset, there's, you know, different reservoirs that are stacked that we want to utilize in different ways and times. And then there's also geology likely below that to be utilized in the same way. That's part of the shift of integrating gas production, you know, thinking and storage, and relating those inseparably together in the Appalachian Basin. That's the business case. In our case, you know, so much concern was talked about this morning about fugitive methane emissions. And, you know, part of our narrative is there's our own new wells. You know, we'll drill 4 wells the first year, about a well a year is what we will need to meet the 6.8 million MMBtu a year of gas that we'll need. And we can, that might be the schedule, might not be the schedule, but in any case, we have new wells, new gathering system, no compression station, a lot of ways that we can monitor very closely for methane emissions and hopefully have some good data that'll put to rest some of the concerns about unconventional gas production in the Marcellus Appalachian Basin anyway, of what fugitive methane emissions are. You can see we have a strategic advantage on proximity to customers. In about a 17 state area, there's no ammonia, urea, hydrogen, no ammonia, urea production, and there's certainly no low carbon, you know, carbon capture storage production of those, nor of hydrogen in that 17 state region. Mentioned this previously. We've gotten tremendous amount of public sector support, as you can imagine, because of the job creation. in that part of Pennsylvania. It's a federal qualified opportunity zone, a new market tax credit zone because of chronic long-term unemployment, Appalachia, former coal mining area, et cetera. Huge economic impact, multi-county. Some of the details, Pennsylvania Manufacturers Association did a study for us that was super helpful to convey that. Some of you might have been a part of these studies a couple of years ago, Forge the Future, and identified some of the petrochemical related potential opportunities. And, you know, ammonia plants are a part of this. I'm not sure hydrogen is even on this list. You know, 2 years is a long time now, a long time ago. Carbon capture certainly is not on this list. That's how fast things have changed. But it'll be there'll not be another petrochemical plant built in America that doesn't have a carbon plan, a carbon storage plan, a carbon capture plan. You've seen these data points of where other petrochemical build out has been around the country. Definitely our turn. I'm sure everybody would agree with that. This just gives a list of hopefully, you know, everybody says you don't want to be first through the door, you know, and people that go first, they're the ones that get murdered. But hopefully we won't be, but here's a list of the first that this project will prove out. And some of our partners in this, they see us that way. We're a way to prove out some of these areas that they're interested in: moving storage, moving carbon, storing carbon, moving hydrogen, et cetera. We'll prove out a lot of that. And by the way, our gas asset is stranded, but we are putting pipeline interconnection in and with the purpose long term to be able to put a hydrogen stream into that pipeline. So the background pieces, this is our schedule. We'll have at least another year of engineering and permitting and construction, hopefully in 2023, about a 2.5 year construction process, which would get us to 2025 commercial operations. One last point related to policy. I really want to make 2 points here, and that's I was allowed and permitted to and honored to be a part of 3 public testimonies in the House and Senate, PA House and Senate last month around carbon capture and storage, hydrogen production, a lot of interest there. So need number 1 right now is education on carbon capture, our geology, which Chris Carter is coming up this afternoon, or after me, I think this afternoon, yeah. And, Pennsylvania, as far as I'm concerned, the expert in state government on geology for storing carbon and storing hydrogen in Pennsylvania. She's been working in this for 15 years. Just an amazing resource. She'll be speaking later. And so the need to educate state government on this is huge, and the need to educate industry is huge on the opportunity. And then secondly, the overall policy need is that there would be a parity in treatment of hydrogen with renewable electricity, blue hydrogen with any other color hydrogen, and that parity and some definitions that are updated. And those kind of encompass what's needed policy-wise to be embrace what's coming. Essentially, a good example would be so that you could take and produce hydrogen from natural gas, put that hydrogen as a blend into the gas pipeline grid, and person X could get credit for that molecule, even though they don't burn that molecule, way away, but the environmental attributes, et cetera, they could get credit for by that blend being injected into the pipeline. That's a good example of policy-wise what's needed in Pennsylvania and on the federal level. So the rest of these are background slides that hopefully will be helpful. And I've zoomed through some of these and hoping to give it to you as background as I gave some context. But I'm more than happy now to take some questions. And if it's time and if you have questions, I'm glad to take them.
Perry, I'll see if there's any questions in the room, and I'll repeat it back to you so you can hear. Yeah, David, go ahead.
So, Perry, being the first, I've got a question of what have been the biggest challenges, and also what have been the biggest positive surprises for you as you've gone through this initial development?
I don't know, Perry, if you could hear that, but what are been your biggest problems and challenges with going through this initial effort?
I think the biggest has been the learning curve.
Surprises too.
the learning curve began in the first meeting I had with the Department of Energy. This was before anything related to carbon capture or hydrogen was in the business case, but it was because the project lies in a federal qualified opportunity zone, and each cabinet level official was under a mandate to facilitate those kind of projects because of job creation, et cetera. And so I sat down with a couple of leaders, Mr. Bennett from Fossil Energy, one of the leaders, and a couple of engineers, and share about the project. And they said, have you considered carbon capture and storage? And we said, no, sir. Have you considered hydrogen storage? And we said, no, sir. I mean, we're completely ignorant and clueless. But you better believe that put us on a journey. And that was a year and a half ago. And blending the business case that we already had offtake, found a market for industrial ammonia and urea for DEF. But then when you add the quote, the low carbon side of the project, it changed everything. So it opened up so many doors and really gives the project a long glide path and ability to weather the energy transition and pivot with the energy transition. And that's the main thing that we're doing right now, is making sure the plant design will maximize the opportunities coming, that we can, there's not a market for hydrogen, blue hydrogen now, like we're describing here. Put it in the pipeline, a power plant use it, even for vehicle transportation, but it's coming. And we're talking to all those kind of parties right now about offtake of blue hydrogen. So, the learning curve has been the main thing. And the places that we would have thought when we first began the project, that would be, we would have the most obstacle, petrochemical plant, new Pennsylvania. But when you blend the low carbon side of it, carbon capture, the fuels that are made, then the whole premise has shifted, where it's a products that were needed. And you can make a case, DEF certainly, air quality in Northeast Mid-Atlantic is impacted greatly by DEF that's been used the last, since the early 2000s, and just huge impact on air quality. And we could make that case for DEF, but wow, we have a green story now that's just mind-boggling. So there's a lot of people in the environmental communities that are close allies with us, that are working toward solutions that don't wreck the economy, but solutions that really do have meaningful emissions reductions. And in the same way that Pennsylvania has led in emissions reductions since 2005, we're going to lead through carbon capture storage, hydrogen production from natural gas. We're going to lead in the next wave of carbon reductions also. It's going to be dramatic. It's going to be dramatic, frankly. I'll stop there. Next question.
Go ahead, Dave. With regards to the storage, the CO2 molecule is probably smaller than the methane molecule. Is there a concern about migration?
I don't know if you could hear that, Perry, but the question was, the CO2 molecule is a different size than the methane molecule. Is there a concern with migration?
Yeah, absolutely. And the whole Class 6 well permitting process that this falls under, and Chris, that'll be speaking this afternoon, can go into minute detail on this. But it's very severe in assessment of the geology beforehand, cap rock, et cetera, for just that very reason. And, as you guys, I'm sure know, that using CO2 and enhanced oil recovery has been going on for 50, 60 years. So lots of experience from that we've already learned from about what happens and how that CO2 moves around. But it's definitely incorporated into the regulations around Class 6 wells. And but it's a great question to further ask Chris this afternoon to get into details of specifically why from geology to geology migration is an issue.
And
any concern over carbonic acid production?
any concern about what kind of acid? Carbonic acid.
In our case, as in my intro, he correctly identified me as a sociologist, so I won't make my engineers on the team faint by getting too far into that. But I don't believe that's an issue at all in our process because of it's a conventional steam methane reformer process, but nobody on our team has ever mentioned that to me as being an issue or process or even a component of what we're doing. And you might know more about this than I do, but that's, I'll be glad to come back with a further answer from the engineers, but I don't think that's an issue. Certainly not one I've heard about in our meetings with my team.
Thank you.
Yep.
So for the operation that you folks are doing, is there a way to certify this natural gas or operation in a clean or sustainable way, given recommendations of, private institutes or other government bodies that can certify this gas as clean? That you could recommend to producers or OEMs?
Harry, is there a way to certify the natural gas so that recommendation that you could give as far as how a producer would do that?
Yeah, there's two schemes, and schemes using it in the European way. They use schemes as through two systems that I've heard about. One's Canadian, one's European, where they're trying to quantify and put into a database and a process in place to certify gas in that way. Everybody heard about the LNG cargo that was turned away a couple months ago from Europe, I believe, from Europe. And that's a bit of an earthquake. So there's work on certification processes right now. I can't recall off the top of my head the name of the Canadian one, but none of them are organized enough yet to be issuing certifications, is my understanding, but it's coming.
Yes.
How receptive are the transmission pipelines to hydrogen blending?
How receptive are transmission pipelines to hydrogen blending?
Well, I know that everybody and their brother are looking at it right now. They're being asked questions from shareholders and E-suites, et cetera. What does all this mean? What are the implications? And it's not like hydrogen has not been blended into natural gas for years in different kinds of settings and applications. But regulation-wise, in practice, what are the implications? Because there's an energy density issue, et cetera, et cetera. But smaller blends are common around the world. But the issue is both the receptivity of the local pipeline system, the utility on top of that, how they're viewing it, what's the value proposition. The ones I'm talking to, they're open to the idea because they're definitely being pressed in that direction. But from the Gas Technology Institute on around, everybody has studied and is studying this to see what it means. I'm sure there's some in the room that their teams are looking at this right now.
Anything else from the room? Okay, Perry, I'm not seeing any more hands. So thank you for your time, Perry. We really appreciate you being virtual and taking the time to talk with us.
My pleasure. I think that you'll be providing the slides to the participants. My email address is there. If there's something that we can collaborate on, or you have another question further, I'll be glad to reach back out to you. Thank you, everyone. Bye-bye.